Hey guys, Mr. Janowski here again. This is the second part of the Chapter 13 slides. So in the last part, we looked at Alpha Centauri, Beta Centauri, and Proxima Centauri, and started to look at how do we measure distances to stars. So we got the ideas of triangulation and parallax, which is an old idea that we've dealt with earlier in the year, and how we use those to figure out the distance to at least the nearby stars. And we learned the formula for parallax, determining parallax, I'm sorry, for determining distance in parsecs if you know the parallax in arc seconds. So we'll continue with this stuff. So let's get started. So one thing you may have noticed is I upped the size of my cursor. So I don't know if you're watching this on your phone. Hopefully that makes the cursor a little bit easier to see. It makes it really awkward to use, but enough about that. So anyhow, this picture. What is this picture about? This is about triangulation. We can determine the distance. We can measure distances that we can't measure directly. So we don't know the distance from where we are to this tree because we can't run our tape measure across this, this gorge here. But what we can do is measure some distance sideways and then measure the angle that the tree appears to have moved by. And by doing that and applying a little bit of trigonometry, you can figure out this distance. So do nearby stars exhibit more or less parallax than more remote ones? Nearby stars will exhibit more parallax. The closer you are, the more parallax you see. However, even for the most nearby stars, the parallax is still really, really tiny. Arc seconds are tiny, tiny angles. They're really hard to measure. It wasn't until 1830 that we were able to measure those angles well enough to actually find the distance to stars using parallax. So what is the formula that relates parallax and distance in parsecs? It is this formula. So if you measure, the thing you're going to actually measure is the parallax in arc seconds. So you look at a distant star, well, a relatively nearby star, and you measure the angle. And then you wait 6 months. The Earth goes halfway around the sun. You measure how that star's position appears to have changed. It's going to be a tiny angle, which you'll measure in arc seconds. Then you plug it into this formula, and you get a distance in parsecs. And a parsec is 3.26 light years, so a little bigger than a light year. So here are the spectra of two stars. So they look kind of similar, but they are a little bit different. So take a look at that. Hopefully that's big enough on whatever screen you're viewing this on to see. What do you notice about them? What's the difference? The difference is the top one is very bright over here at the violet end, but it's dimmer over here at the red end. And the bottom one, it's the opposite. This one is very dim at the violet end, and it's very bright over here at the red end. So these are actually the spectra that we see in visible light of two stars, Betelgeuse and Rigel. So take a look at these two spectra and decide which of these spectra goes with Betelgeuse and which one goes with Rigel. So Rigel, the bottom star, is the top spectrum, and Betelgeuse, the top star in this picture, is the bottom spectrum. So convince yourself that this works. So let's look at Betelgeuse first. This spectra here that is very bright towards the red and dim towards the violet. It's not that the violet is not there, it's just that it's dim. But yeah, stronger in the red. Well, look at Betelgeuse. Betelgeuse appears red. Betelgeuse, of course, it's been in the news lately. It had been dimming very dramatically, more so than it had been the entire time we'd been measuring it. But it has actually kind of started to brighten up again. So we don't think Betelgeuse is about to explode. There's different theories about why that actually happened. But yeah, it looks like we're going to have Betelgeuse at least for a little while longer. So anyhow, this spectra, brighter at the red, dimmer at the violet. Well, look at the star it came from. Yeah, it's visibly red. If you see Betelgeuse at night, it is visibly red. And especially if you compare it to Rigel. So Rigel down here, dimmer in the red, but brighter in the violet. Well, Rigel actually looks, kind of violetly blue. It looks blue if you actually see it. So yeah. So we study color and brightness of stars to reveal fundamental features about their structure and their history. So where are they in their, the course of their life? So we can learn a lot about these two guys just by measuring their color and brightness. So you can usually figure out the object's temperature just by looking at its emitted light and looking at it very carefully. So we've talked about this before. You look at all the wavelengths you're getting, you figure out, well, where's the peak wavelength? And then you plug it into this idea. This is Wien's law. And this just spits out, well, what's the temperature of the surface of the thing you're looking at? So yeah, we've done Wien's law before in black body radiation. So that idea is back again. The book actually does a really good job of teaching you things and then bringing those things back up again. Yeah, I like the book. So on to this idea of luminosity. So luminosity is the amount of energy an object radiates each second. So it's the rate at which this thing is using energy or putting out energy. So if you have an ordinary household bulb, the old-fashioned incandescent kind, it might be using 60 watts of power. So its luminosity would be 60 watts. If you go out to the overhead parking lights, those are much brighter than the bulbs you put in the lamps in your house. Those might be 1500 watts. So 25 times brighter. If you compare that to the sun, well, the sun is crazy, crazy bright. It's got this huge luminosity. It's putting out a ton of energy, and it's doing it by fusing hydrogen into helium, which we learned in last chapter, chapter 12. So why is this important? Luminosity, the amount of energy that the star is putting out, is very much related to the rate at which it's consuming its fuel. So how much energy it's putting out tells you how quickly it's kind of eating itself up. So you need to know its luminosity if you're going to decide things about its lifetime, where it is in its lifetime, how much longer it's got left to live, things like that. So luminosity is also very important for measuring a star's distance and radius. So luminosity works by this. This is an inverse square law. In the sciences, especially physics and astronomy, we love inverse square laws. Gravity works by an inverse square law. The intensity of sound, well, that gets complicated, but yeah, it also works by an inverse square law. So yeah, the inverse square law is going to relate an object's luminosity and its distance to its apparent brightness, which is how bright it looks to us. Again, in astronomy, there is a difference between luminosity and brightness, even though in regular everyday speech, those are kind of very much synonyms. So in this picture of the Arc de Triomphe in the Champs-Élysées, so pardon my French there. Yeah, you see all these streetlights, heading towards the Arch of Triumph. And yeah, these are all identical bulbs, so they're all equally luminous. All these bulbs are identical. But the one that you're standing closest to, well, we would say this one is brighter. Again, the bulbs are identical. They're all putting out the same amount of energy. But the one that's closest to you, we would say, is actually brighter. So equal luminosity, but this one is brighter. And that obviously depends very much on where we're standing. If we were standing closest to this one would be the brightest. This one would be the brightest. If we were standing all the way down here, this one would be the brightest, and this one would be the least bright. And no matter where we're standing, they're all equally luminous. So more on that in a couple slides. Back to the inverse square law. So light spreads out in all directions. So this is a very two-dimensional kind of drawing, but it's actually spreading out in 3 dimensions. So if you think, this is helpful that I made the big cursor. If you're standing near the streetlight, so imagine this cursor is kind of the size of your eyeball. So if I'm standing pretty close to this streetlight, I'm getting at least 2 of these lines going through my eyeball. Come back, cursor. If I'm standing much further away, so the lines in the drawing obviously don't go out that far, but if I'm standing much further away, I wouldn't have 2 full lines going through my eyeball. So my eye would be collecting less light, and it would look less bright to me. So we can also understand this in terms of photons. Again, photons are the particles of light. So imagine you have a light source. So here's a light bulb here, and you draw these transparent spheres all the way around the light bulb. So the spheres aren't eating up any of the light. They're just letting it go through. Now notice these spheres, it's only a quarter of it is shown, but the sphere goes completely around the light bulb. So any light that leaves this bulb has to go through this sphere and through this sphere and through this sphere. So The amount of light going through each sphere is the same. However, the spheres keep getting bigger and bigger. So you're getting less light per area going through each sphere. So if you can imagine having some kind of light detector, maybe this is your telescope, and it's this distance away, you've got 36 photons from the light bulb hitting this, this 1 square meter collector right here. If you go twice as far away, if you wanted to collect 36 photons, your collector wouldn't be twice as big. It would have to be 4 times as big. That's the idea of the inverse square law. So yeah, all of the squares in all of these pictures, the little squares are all the same size. They're all 1 meter by 1 meter. And if you're close, you're getting a lot of photons through that. And if you take the same collector a little bit further away, so now this guy here is getting 36 photons. If we move twice as far away, the same size collector, so just think of one of these little squares here, it's only getting not half as many, but 1/2 squared. It's getting a quarter as many. So it's only getting 9 photons in this case. And if you compare this guy here to this guy here, so we went from 1 meter away to 3 meters away, so we're 3 times as far away, you're not getting 1/3 as many, you're getting 1/3 squared as many, you're getting 1/9. So 36 photons per square meter here, 9 photons per square meter here, and only 4 photons per square meter here. So that's the idea of the inverse square law. And this all works because we live in a three dimensions of space kind of universe, is what inverse square laws come from. But it's all based on the idea of the surface area of a sphere. The formula for that is 4 pi r squared. Here we're using d because it's the distance you are away. It's still the radius of the sphere. So yeah, it's an inverse square law. So here's your formula that relates brightness to luminosity and distance. So luminosity is just how much total energy this thing is putting out. It's just a property of the thing itself. Brightness is different. Brightness is how much of its light are you getting. So to figure out how brightness relates to luminosity and distance, it's basically just going to be luminosity divided by the surface area of the sphere that, the imaginary sphere that you're standing on to look at the thing. So yeah, let me go back one. Yeah, so why is it called an inverse square law? It's because brightness is proportional to the inverse of the distance squared. It's an inverse square law. So the way this works, this is how a lot of math works. 4 and pi are just numbers. Those aren't going to change. B, brightness, L, luminosity, and D, distance, those can change. Those would be our unknowns. So you've got 3 unknowns in this little relation here, this equation. If you know 2 of them, you can figure out the other one. So typically, you measure brightness directly using what's called a photometer. It's a light meter. It's measuring how much light you're getting from a specific thing. Distance, you might know because you're able to measure it by parallax if it's a nearby star. If that's the case, then you can measure the luminosity. It's also possible that you know the luminosity from some other method, which that's just going to have to be mysterious at this point. We'll learn about what the other methods are later in this chapter. But yeah, you can measure the star's brightness. And if you have some clever way of figuring out what its luminosity actually is, then you can figure out what its distance is. Very useful if its distance is too great to be measured using parallax. So your average star has a luminosity that's pretty close to the luminosity of the sun. We would say it's within an order of magnitude, within a factor of 10. It might be 1/10 as bright. It might be 10 times as bright, but it's kind of in the same ballpark. There are some stars that are actually millions of times more luminous than the sun. They're actually putting out millions of times more light than the sun. And there are some that are only, 1,000th as luminous as the sun. But most of them are pretty close to the sun. The sun is fairly typical in this regard. So this idea, the difference between luminosity and brightness, again, in everyday parlance, in the parlance of our time, they're kind of similar ideas. They're synonyms. In astronomy, they mean different things. So luminosity, in plain English, luminosity is how bright the object actually is. Again, it refers to how much light energy the thing is actually putting out. And it doesn't matter if anyone's looking at it, or if they are, how far away they are. It's just a property of the thing itself. Brightness refers to how bright it seems to be. It's often called apparent brightness. This very much depends on where the observer is. So if you have a star, the star is as luminous as the star is. If you get close to the star becomes brighter. It doesn't get more luminous. It's still putting out as much light as it always did, but it becomes brighter because it appears brighter if you're closer to it. So again, in this picture, all of these streetlights, if they're all identical bulbs, they're all equally luminous. They're all putting out the same amount of light. However, the ones that you're closest to, you would say are brighter. So that's the difference between luminosity and brightness. So, quick review. What is the law that lets you determine the temperature of a star by observing its light? So this is an oldie but a goodie. This has come up a couple times this year. That law is Wien's law. So measure the light you're getting from the star, figure out where the peak wavelength is, plug it into this formula, and it tells you the temperature of the star. So what term did we just learn that is the amount of energy an object radiates each second? Is it luminosity or brightness? It is luminosity. So again, luminosity, you can think of it, that's how bright it actually is. Brightness is how bright it appears to be, which is the answer to this question. What is the difference between luminosity and brightness? Luminosity is how bright the object actually is. Brightness is how bright it appears to you. So again, all of these streetlights, they're equally luminous. The ones that you're closest to, you're going to say those are brighter because they appear brighter to you where you're standing. So what is the formula that relates brightness, luminosity, and distance? It is the inverse square law. Brightness is equal to luminosity divided by 4 pi d squared. So again, it's called an inverse square law because brightness is proportional to the inverse of d. D is in the denominator here, squared. So that's an inverse square law. That's it for this part of the slides. Hopefully you guys found that helpful.